Hello. So, in the last classes, we discussed about kinematics. So, just a recap, like mechanics, it has two parts. One is kinematics, it deals with how objects move, and dynamics is like it deals with the force and why objects move as they move. Like it deals with the force and motion. Okay. So force sometimes means force is like it is any push or pull on the object. It is defined as the push or pull on an object. Okay. And it's the ability, basically, it is the ability to cause a change in the state of motion on an object. So it is the ability to cause a change in state of an object. Okay. And so force causes acceleration. Okay. Basically, it has ability to cause an acceleration. It doesn't always causes acceleration because but it has ability to cause acceleration, and the mass is the measurement of how much it opposes the acceleration. So it is the measure of how much it can oppose the acceleration. So the force has the ability to cause the change in state of motion on object, but it doesn't always causes the change. Like, so when the it doesn't cause acceleration when the uh, net force acting on an object is zero. If the individual forces are still there. Suppose if a book is lying on the table, the force of gravity is acting downwards, but it doesn't fall down because the contact force or the normal force which the surface exerts on the box is acting upward, and Fn, the normal force which is acting on the book due to table, is equal to the weight of the book acting downwards. So both of them are balancing. So though there is a force, but it is not causing acceleration. So force has the ability to cause the acceleration, but it doesn't always cause because the net force is zero. So in this, the upward normal force from the table is equal to the force of gravity, and that's why these forces are equal in magnitude and opposite in direction. So that's the reason the net force is zero. So force has the ability to cause acceleration, but it doesn't always cause the acceleration. Thus the sum of all the forces acting on an object is calculated as the vector sum of individual forces. So if the vector sum of individual force or the net force is zero, then it doesn't accelerate or it doesn't cause acceleration. So zero net force is equal to zero net acceleration. Okay. So, and mass is the mass resists the acceleration. So the greater the mass, the less the ac- acceleration. Okay. So an object at rest to become with the Newton's first law, which states okay. So Newton's first law of motion is an object at rest will remain at rest and an object in motion will remain at a constant velocity unless acted by net external force. Okay. So an object at rest will remain at rest unless acted by a net external force. So an object will remain at rest until we have an external force uh, of net external force of zero acting on it. So, so still we can, if an object is at rest, we cannot, and we can still, there may be a force acting on it. It's not that no force is acting on it, but the net force is zero. So you can, it simply means that we can add up all the forces and we get a value of zero. And so the net external force is zero, then it will not move. Okay. And another thing is an object in motion will remain at constant velocity unless acted by a net external force. So, because velocity is a vector, so an object will maintain a constant speed unless at constant speed and direction unless acted by a net external force. So again, this doesn't mean like a car is moving at a constant velocity. Then we say that okay, because it is a constant velocity, net external force is zero. It doesn't mean that there is no force acting on it, but it has a constant velocity and the same direction. So there is no direction change and there is no speed change. The net external force is zero. That's why it will continue to move in the with the same velocity. So it's like in this way, suppose if we take a case A, like a bus is moving with the speed of 20 meters per second and it keeps on moving in the same speed, then in a same direction, then net external force is zero. But a bus was moving 20 meters per second and then it moves 25 meters per second. In a second, it increases to 20 to 25 meters per second. Then there is an acceleration because the velocity is now not constant, though the direction is same. In the previous one, the velocity and the direction both were same. In this case, the velocity has increased, though they are in the same uh, direction. So there is a F net. There is a net external force. Okay, it's not equal to zero. And suppose if a car is moving uh, and making a circle, a sort of making going in an arc, it is changing the direction, but the speed is same. Then also we say that, but it is changing the direction. Then also we say there is a net external force. So net external force is not equal to zero. So now another conceptual problem is like suppose a school bus is moving with a constant acceleration, okay, and uh, okay. and the backpacks are lying here. And when the driver presses the paddle and it comes to a sudden stop, then why do the backpacks they move forward? Okay. Then all the backpacks they move forward when the school bus comes to a certain stop. So why it happens like so the backpacks they move forward because of the inertia. Okay. It is the tendency of an object to resist the change. Change in its state of. Okay. So the backpacks in because of the Newton's first law of motion, the backpacks the will still move as the school bus was moving. Backpacks will still move, and it will continue to move in the forward direction until so no external force in this is acting on the backpacks. Here in for the school bus, as the driver puts the brakes on, the net external force is applied and the bus comes to stop. But there was no external force on the backpacks. So it continues to move in the it continues to move forward, but it eventually they come to stop because the net external force, like the friction force with the floor of the bus, causes the backpacks to uh, slow down. So the what is the Newton's first law is also known as law of inertia. Okay, so law inertia, it is the tendency of an object to resist change and in the state of motion. So the object in motion will stay in motion unless an external force applies on it. So when the bus was moving, the backpacks were also moving. So as as we apply uh, as the driver applies brakes, bus comes to stop, but the backpacks, because there was no external force on backpacks, it continues to move until it is the friction force of the bus stops it. Okay. So when the bus brakes, the backward force acting on the bus causes it to slow down, and those the backpacks don't immediately feel this force, and that's why they want to continue moving forward. And because the bus slows down, backpacks continue moving forward. It seems as the backpacks are moving forward relative to the bus. And then the friction between the backpacks and the floor, they eventually apply so a force to backpacks and slows them down. Okay. So now the Newton's first law doesn't uh, hold in every reference frame. Okay. So, like we saw the backpacks on the bus. So it doesn't. Newton's first law act holds on only to the inertial reference frame. Like, okay, so in accelerating reference frame, like the bus was moving, the backpacks in the bus, the Newton's first law doesn't hold because the backpacks were still moving without any net external force on the backpacks because they were on the accelerating reference frame. So, so Earth is like a inertial reference frame because though Earth is moving, its speed is Earth is still rotating, but its speed is very less as compared to the objects like car moving on it. So Earth we can consider it as a inertial reference frame. So usually we consider Earth as a uh, inertial reference frame. So any reference frame that moves with a constant velocity relative to inertial reference frame is also considered a inertial reference frame. Like we know Earth is an inertial reference frame, and anything moving with a constant velocity, suppose if a bus and it is moving with a constant velocity relative to Earth, then that can be also considered as a inertial reference frame. But this doesn't happen because we cannot assume that a bus is continuously moving in a same speed for forever. So, okay, but like a car moving, that is considered the accelerating reference frame. So, a car, so Newton's first law doesn't hold on to the objects lying on the car. So, if the net force on a body is zero, the velocity will not change. If we assume that there is some object and traveling in the space with some velocity and speed in and also in some direction, and it has no gravitational interaction, there is an absolute vacuum in the space. So this thing will continuously travel. It will continuously move or travel forever. So an unbalanced force on this object will impact its velocity. It may not impact its speed, but it will impact its velocity, and uh, that will impact its travel. So we can take an example of a skater. Suppose a skater is moving in a circular direction, in a circle, and it's skating in ice ring, and it catches the hold of the rope nailed to a stake. So direction is going to change, and it So direction is going to change and it's going to go in circles as long as he is holding to uh, the rope. So velocity changes, however, the speed is same because we assume it's a very little resistance because there is snow no, or it's ice. So the force, the inward force, which is because of the tension from the rope, is pulling on the skater and the direction might have changed. So as we know, force is a vector quantity. It has a direction and magnitude both. And it is represented by an arrow. So the length of the arrow shows is gives us the idea about its magnitude. So here the force, inward force or the tension from the rope is pulling on the skater and that direction would have changed, keeping the speed same. So another example we can take is like the moon, and this is a planet and the moon is revolving around it. So reason it keeps stays in the orbit because the pull of gravity keeps making its direction changes. It and it changes velocity but not the speed. So the inward force of gravity is going to accelerate this object as when it travels. So if the planet was not there, it will keep on going in the direction. Okay. So it may if so if planet was not there, it will keep on going in that direction forever and ever. So because okay. So it has the exact right speed. So it doesn't go off into deep space like this. Okay. And or it doesn't fall off like this, or it doesn't fall into the earth. So unbalanced force on a body will always impact its velocity. It could be speed or direction or both. This is not like this. So the reason why initially moving object tends to come to rest in our everyday life is because they are being acted on by the unbalanced force. So suppose this is a table. So if a block and slide, okay. So if a block slides across the table, and the reason it comes to stop is because of the friction, because the grinding of the surface of the book with the grinding of the surface of the table. Yeah. And another example is like if I throw a stone in the pool, okay, and there are no currents, the stone eventually comes to a stop because of the resistance of the water itself. So the resistance of the water is providing an unbalanced force in a direction opposite to the direction of the motion. And that's what is slowing it down. So unbalanced force on the body may not change its direction or may just accelerate or may deaccelerate it. Now suppose um, so what net force is required to maintain a 5000 kg object at a constant velocity of 6000 meters per second. So what net force is required to maintain object? Okay. So according to Newton's first law, an object will continue in its state of motion unless unbalanced force acts on it. So no force is required here to move it at a constant velocity. So F net is net force here is 0. Okay. Because there may be forces acting on it, which is like suppose the applied force and the friction force. Okay, but they may be balancing each other, so there is a constant velocity. There is no acceleration. Acceleration is 0. That's why net force is also 0. So, like another example we can take is like sun and earth. So, it's a sun and earth is relatively small. Okay. So Earth is moving relatively with constant speed. Right? It's a relatively constant speed um, around the sun. Okay. So it's constantly changing its direction. Okay. It's a perfect circle. Okay. So it's constantly changing direction because of the gravity, the gravitational field acting on the Earth Okay. And okay. So the gravitational force acting on the Earth generated by the sun causes to pull the Earth towards the sun. And so instead, like Earth is traveling out of the space, it changes the direction. And the Earth also exerts gravitational field on the sun. And these two forces are equal. They're equal. And as we now will study later, the Newton's third law, for every action, there is a reaction. So the forces, force, so the forces, they don't have to speed up or slow down. It can also change the direction, as in this case. Okay. So if we see that Earth is here, Earth moves relatively in the constant speed around the sun, and it's constantly changing direction because of the gravity, the gravitational field which is acting on Earth uh, causes uh, pulls Earth towards sun, and so instead, like the Earth, which may travel out of space, it changes the direction and and it moves around the circle. So in the next class, we'll do the Newton's second law. We'll study about the weight and mass, the difference between. So let's see. Thank you.